Hi, Assalamualaikum. I am Nur Wardina binti Ishaq and my group mate are Ahmad Muklis bin Yusuf, A24KT0026, and Rabiatul Adawiyah binti Muhammad Zar, A24KT0238. We are Group 7 from Section 4 and our lecturer are Dr. Muhammad Asmadi bin Muhammad Yusuf. We will explain on the flash separation design of methyl ethyl ketone 1 to toluene 2. Flash separation is a single-stage distillation process that separates a liquid mixture based on difference in volatility. When a pressurized feed stream enters a lower pressure flash chamber, a portion of it instantly vaporizes. The more volatile component, lower boiling point, concentrates in the vapor phase, while the less volatile component, higher boiling point, remains primarily in the liquid phase. For this project, the binary mixture consists of methyl ethyl ketone, MEK, and toluene. MEK is the more volatile component due to its lower boiling point, meaning it will enrich the vapor stream. This specific separation is widely utilized for solvent recovery and purification in the chemical, paint, coating, and adhesive industries. Following the project guidelines, this binary system is evaluated as an ideal solution governed by Raoult's law. The objectives for this project are to study the flash separation process for a binary mixture of methyl ethyl ketone, MEK, and toluene. Next, to review the typical process conditions, including feed composition, operating temperature, and operating pressure for the separation of a MEK toluene binary mixture. Lastly, to calculate the moles of vapor, moles of liquid, liquid phase composition, and vapor phase composition using flash separation.
An equimolar feed composition consisting of 50 mol% methyl ethyl ketone and 50 mol% toluene was selected. The flash separator was operated at a temperature of 95.1 degrees Celsius and a pressure of 1 atmosphere. The selected temperature was chosen because it lies between the boiling point of methyl ethyl ketone, which is 79.6 degrees Celsius, and toluene, which is 110.6 degrees Celsius. In addition, 95.1 degrees Celsius is approximately the average of the two boiling temperature. Under this condition, partial vaporization can occur, allowing the separation of the binary mixture through flash separation. Several assumptions were made to simplify the flash calculation. First, the methyl ethyl ketone toluene mixture is assumed to behave as an ideal solution, allowing Raoult's law to be applied. Second, vapor-liquid equilibrium is achieved inside the flash separator. Lastly, the flash separator is assumed to operate at a constant pressure of 1 atmosphere with negligible heat loss to the surrounding. This process flow diagram shows the flash distillation of an equimolar methyl ethyl ketone toluene mixture. A basis of 1 mol feed is used, containing 0.5 mol methyl ethyl ketone and 0.5 mol toluene. The feed entered the flash distillation column at 101.325 kPa and 95.1 degrees Celsius, where it is separated into vapor and liquid stream.
For the flash calculation, we start off by listing all of the constants for entering equation to find the vapor pressure for each substance from table B2 in the Introduction to Chemical Engineering Thermodynamics 9th edition books. By substituting all of the constants into the ensuing equation at temperature of 95.1 degree, we will get the P saturated for MEK is equal to 162.125 kilopascal, while the P saturated for toluene is 63.865 kilopascal. To determine whether the mixture is in two-phase region or not, first we need to find the bubble point pressure and the dew point pressure for the system. By substituting the value into the equation, we will get the bubble pressure of the system is equal to 112.995 kilopascal, while the dew pressure is 91.633 kilopascal. The system operates at standard condition, which is 101.325 kilopascal, which is in the between of the P bulk and P dew. So the mixture is in two-phase region. Next, we need to determine the K value for each substance to find the vapor and liquid molar fraction. From Raoult's law, we will get the value of K for MEK is equal to 1.6, while toluene is equal to 0.6303. We will continue by finding the vapor and liquid mole fraction. For the liquid phase mole fraction, we will use the saturated pressure for both of the substance and the system pressure. By substituting all of the value, we will get the liquid phase mole fraction of MEK1 is equal to 0.3812, and for toluene we will simply just subtract it with 1, so we will get the value of 0.6188. For the vapor phase mole fraction, we will use the K value we find before and simply multiply it with the liquid phase mole fraction. We will get the vapor phase mole fraction for MEK is equal to 0.6099, and for the toluene we will get 0.3901 mole. To find the vapor and liquid fraction for the system, we will use the Radford-Rice equation. By substituting all of the value into the equation, we will get the value of vapor fraction is equal to 0.5191, and the liquid fraction is equal to 0.4809. The system will tend to vaporize rather than condense since the vapor fraction is larger than liquid fraction.
To construct this PXY diagram, we assume ideal solution behavior and apply Raoult's law. Using the saturation pressures of our two components, we calculated the bubble pressure across the liquid mole fraction ranged from 0 to 1. We then determined the corresponding vapor phase mole fractions to plot the due pressure curve showing the phase envelope where vapor and liquid coexist. In this project, the vapor-liquid equilibrium behavior of a binary mixture was successfully modeled at a constant temperature using Raoult's law. By calculating the saturated vapor pressure, which is equal to 162.125 kPa and pressure 2 is equal to 63.865 kPa, the system phase characteristic were established across all composition. This results in PXY diagram that successfully validated ideal VLE behavior. Ultimately, this project demonstrates a practical application of chemical engineering thermodynamics, providing the foundational phase behavior data essential for designing industrial separation and distillation process.
Last but not least, this is our reference for this project, which is the Introduction to Chemical Engineering Thermodynamics 9th edition. That is all from us. Thank you.